I'll be explaining the oxygen-hemoglobin dissociation curve. On the y-axis, we have hemoglobin saturation percentage, while on the x-axis, we have the partial pressure of oxygen. So, you see during the first 7 mm partial pressure of oxygen, the hemoglobin saturation is slowly increasing. That is, hemoglobin is slowly being filled with oxygen until 70, after being filled with oxygen. After like this, it will go very slowly, like it will take like 100 or 110 or 20 for it to reach only like 10% more, till like 89% it is filled at 70 mmHg. While after this, it takes about a lot of partial pressure to get filled till 100% saturation of oxygen in hemoglobin. Why is this very helpful to us is because, like, if someone has a lot of blood loss, despite the oxygen level be decreasing in the body, that is the partial pressure of oxygen dropping, the hemoglobin is still fully saturated. It's still saturated to a high limit, so it can supply the body without problem. It is a big problem after it falls below 70 mm of partial pressure. This is the point that our body sees the red flag, and like the hemoglobin saturation start decreasing, and then the body functions get affected. So in the hemoglobin oxygen dissociation curve, we have the right side and we have the left side. There's a very important concept that is most likely asked in papers. So on the right side, it's like, consider this, that you're in the tissues. Carbon dioxide concentration is high, right? And the hydrogen ion concentration is also high. And due to these two factors, 2-BPG production is also increasing here. And since we're in the tissues, like for example, consider the state of exercise. We're exercising a lot, so our tissues have like a deficient supply of oxygen, so we need a lot of oxygen. Bohr's law apply here, that is, the deposition of oxygen occurs in the tissues. Like, since we know that oxygen or any other gas move from high concentration to low concentration, they move from the blood where they're in high concentration, that is bind with hemoglobin, to low concentration in the tissues where carbon dioxide and hydrogen ions are more. So they will move there, and hence, since they're getting deposited there, hemoglobin dissociation or hemoglobin affinity for oxygen prominently decreases. On the other hand, if we go look at the left side, we see the very opposite of that. This is when we're in the lungs. In the lungs, as we know, when we breathe in air, oxygen concentration is high, carbon dioxide concentration is low, hydrogen ion concentration is low. Due to these two factors, 2-ppg production is also decreased. Now, the Haldane's law is, in the Bohr's law, we had the deposition of oxygen in the tissues. Here we have the deposition of carbon dioxide in the lungs. Since carbon dioxide concentration is high in the blood capillary that's delivering it to the lungs, but is low in the lungs, it will move into the lungs, and oxygen will bind to hemoglobin. Hence, hemoglobin has high affinity for oxygen in this case.